Hey there, in this video I'm going to talk about stretching and compression. So to start with, let's take a spring for example. This is a spring. And another one, this spring I stretch it. And the third one, so I draw a line here. So I will put 1, 2, and 3. Okay? So the first diagram right here is the original length of the spring, which this line right here, this line shows us that this length is the initial length or the original length of the spring. So let me just erase this arrow. So notice that the second diagram right here, it has extension in it. The reason is because if I add an object here, which is an object which has mass, an object which has mass, if you have mass, you have weight. So weight is equal to force, so the force right here is pulling the spring, so it will cause extension in it. And furthermore, the third diagram right here, it has more extension in it. The reason it's the same is just that when you add more weight on it or more force, you will have more extension. So this principle brings us to the Hooke's law. So Hookeslaw. Hooke's law. So the principle of Hooke's law is a material obeys Hooke's law if below the elastic limit, the extension is proportional to the load. Okay, means force. Okay, so a material obeys the Hooke's law if below the elastic limit, the extension is proportional to the load, which is force. So Hooke's law, it has its own formula, which is F equals to Kx. So the F here is the load, which is in force, and the K is the constant, the spring constant. And the X right here, it's the extension of the spring, okay? So the spring constant right here, it's the K, which is the constant, the gradient. And the load right here, it's the force, the extension, which is how much the spring has extended, okay? And again, I'm going to draw a spring. Like just now, 1, 2, 3, a spring like just now. Okay, and I'm going to draw a line to show us the initial length of the spring. So this is the initial length of the spring, okay? Initial length. Okay, and again you will notice that let me label the numbers and again there is extension in the second diagram right here. The reason it has extension is because we have a force. Let's say if I put an object here of 1 Newton of force, the extension will be 10 millimeters. Okay, so based on the formula right here, if we have more extension, which means we have more force. Okay, so right here we have more extension, which means we have more force. And I'm going to put an object here again, the same object. Let's say it is a metal object, which again 1 Newton and more force, right? Let's say I add the same object. Same object means same weight means same force. So there is force pulling it downwards, which means we have 1 Newton of force pulling the spring. Right here, the total force is 2 Newtons. Okay, so let us just look at this F equals to kx formula for a while. Okay, so F equals to kx. So right here, the initial length, which is the original length of the spring, it is not the extension, so the extension will be 0, which means no extension means no force. Okay, or no force means there is no extension. Okay, so right here the constant will be 0, okay, because there is no extension in it, there is no force. Let's try another one, F equals to kx, the diagram number 2 right here. So right here we have the extension, which is 10 millimeters, the k, and the F, which is 1. So this 1, 2, 3 diagram, it's the same spring, it's just that I add different weights in it, we have different extension. It is the same material, it is the same spring. So which means we have the same constant, right? The same constant. So let me just prove it to you. The k, it is the spring constant. So if we move the 10 right here, so 1 over 10, which is 0.1 equals to k. So this is the constant, and the unit of this, let me just erase it for a while here first. Okay, let me just erase everything. Okay, so let me just redo it. F equals to kx. So 1, which is the force, the load, and the k, it's the spring constant, and the x right here, it's 10 mm. Okay, so 1 Newton divided by 10 mm. So 1 over 10 and m, which is 1, right? So if you divide by 10, so 0.1 Newton per mm. Okay, so this is the constant. It is the gradient of the spring. So as I said just now, it is the same spring which is have the same constant. So and again, F equals to kx. The force here is 2, the k is the constant, and the x here, this will be 20 mm. Okay, 20 mm. And 20 mm divided by 20. So and again 2 over 20, it's 1 over 10. So 0.1 mm. Okay, so it is the same constant, which is the same material, the same spring of this result. So let me just erase this. We can plot this into a graph. That is why I use this template today. So let me just draw a graph. Let's plot this into a graph. So the graph here, this is a graph. Okay. So I just want to talk a little bit about a graph. So a graph, we have independent and dependent variable. So right here, we will call it as the x-axis, which is the IV independent variable. And right here is the dv dependent variable. Okay, so in this case, the independent variable will be the load. Because load is independent, we can add as much load as we want. No one can control us. So you will notice that all of those speed time graph, the time will be in the x-axis, because we can't really control time. Time is independent, so no one can control time. Time is independent. That is why it is in the x-axis. So let me just erase this time. So the load is going to be the independent variable of the load, okay, in Newton. And this extension will be here. So this will be the extension. Hold on, I need more space. Okay, this will be the extension, so the units will be mm, right, millimeters. So I'm just going to move this word a little bit because I need more space. So look, I will just put it here. Okay, and I'm going to label it. I'm going to put in all those numbers in 1, 2, 3, 4, and even 5. Okay, so right here the extension will be 10, 20, 30, 40. Hold on, I need more space. And I'm just going to move this guy, and again I'm going to move it away first. Okay, I'm going to move it somewhere else. Let me just move this whole graph. Okay, I'm just going to move my graph like this because I really need more space. So I'm going to move this extension word to the right a little bit. Okay, to the right. Okay, so it's perfect right now. So 10, 20, 30, 40, 50, and 60. Okay, and so on. So let us just plot the graph right now, okay? So before we plot this graph, I just want to say that in this Hooke's law graph, it's always start from 0, okay? Always start from 0 because f equals to kx. If there is no force, there will be no extension, okay? So right here, there is no extension, right? In this first diagram, this number 1 diagram, there is no extension, which means that there is no force. So 0, 0. So I will just plot my first point here. First point will be 0, 0, okay? Now I'm going to erase this. And the second one, we can plot it in. So the extension will be 10 mm, so we'll be somewhere here and with the force of 1 Newton. Okay? And again, the next one will be 20 mm, and the force will be, the load will be 2. So if you want to further add weights on the spring, we can further plot it like this, okay? Further plot it. But there is a limit, so let me just draw a straight line here. Okay, just draw a straight line. Okay, just let me draw a straight line. And I'm going to erase this a little bit. Okay. Okay, so this will be our straight line. So if we further add weights on it, this graph we can plot it like this in a straight line, okay? The straight line graph. But slowly this graph will like this. Slowly change to a curved one. Okay? Slowly be a curved graph. Okay? So because there is limit for the spring to extend, okay? So if we add more and more and more weights on it, slowly the spring will become longer, right? More extension, longer, and longer. So if right here, let's say we have 10 newtons of force or 20 newtons of force, so normally if we release the weight, if we release the force, the spring will automatically go back to its own original length, right? So in this case, it has crossed the elastic limit, okay? So let me just erase this spring for a while, just a quick one, Let me draw a line here, okay? Draw a line here, draw a line here, okay? So this line is not nice, okay? Just a quick one. Okay, so I'm just going to name this as point X, okay, point X. So there is a name for this point, a special name we call it as elastic limit. Okay. Elastic means when you stretch something or you compress something, it will go back to its own original length, original form. But when it crosses the elastic limit, it will not go back to its own original length and original form. And also we can call this as limit of proportionality. Okay? Limit of proportionality. And another thing is that anything below this x, it will obey the f equals to kx, which means it will obey the Hooke's law. So anything crosses this line, crosses the point x right here, it will not obey the Hooke's law. Cross. Okay? So in this page, I have talked about the spring, the stretching. So right now, I want to talk about compression. But it's the same. Okay, let's say we have a can right here. Okay, let's say we have a can right here, a metal can. If you compress this can, if you compress it with lower force, it will not cross the elastic limit, right? If you compress it very lightly, very gently, it will go back its own original form, right? But what happens if we compress this can with a greater force, okay? With a greater force. So if we compress this can with a greater force, this can will be dented, right? Dented can. Okay, so will be something like this. Okay, something like this. If you compress it with greater force. Okay, if you compress it with a greater force, if it crosses the elastic limit, if we release the force, it will be this. Permanently, the metal can will be like this, in this form, okay? But in this case right here, if we apply lower force to compress it, lower force gently, it will not cross the elastic limit, which means it still obeys the Hooke's law, which means it does not cross the elastic limit and it will go back to its own original form. So this will be our permanent form. Okay? So as long as you compress it with lower force, it does not cross the elastic limit, then it will go back to its own original form. Okay? So that's it for this video. I hope you have understood what I had just explained just now. And do remember to subscribe to my channel to enhance my channel's algorithm. And I will see you in the next one. Bye!